Well, today we're going to wrap things up. This is our last official class. And then we have our exam on Thursday of next week. So let me share with you the calendar. Here's the calendar. Today we're going to wrap up chapter 9. We're going to talk a little bit about correlation and regression testing. So we've been able to find a correlation and a linear regression line. And now we want to test to see what our sample is saying about the population. That's going to be the last thing that we do in chapter 9. Then there's no class, right, at all, or no even, well, if you want to come see me during office hours, it's okay, but there are no classes next week until our test on Thursday. Now, I did change the homework due date so that the homework will be due on Wednesday night at midnight, the night before your test. And of course, your test, even though it was planned for just a regular class period, I'm going to open it up from 8 until noon on Thursday so that you have plenty of time to get it done. And if you have any trouble uploading your work or any computer problems or things like that, we'll be able to get them resolved. To take your test, you'll need to log into the Zoom meeting and say good morning, and then you can get started, and I'll kind of proctor along as you and be standing by to answer questions if you have any questions about it. I think that that's it for administrative things. I'll send out a little announcement about the test here maybe this afternoon, and everything else should be done. So if you want to get a few more homework points, you certainly can go back and do that. And if you do end up with any questions or problems as you're wrapping things up, be sure to send me an email right away. We have to have everything done, finished, wrapped, so that I can turn in the grades by Thursday of next week. Anything coming to mind that's bothering you right off the get-go here?
No, I don't think so.
Okay. Okay, well, today we want to pick up, when we were looking at chapter 9, you probably noticed that Larson did some hypothesis testing kind of throughout the 3 sections, and we saved it all to the end. So that's what we want to talk about today. So the first thing I'd like to do is go back to our notes and take a look at section 1, 9.1. And so today's kind of a review day and pick up the pieces that we missed today. That's what I'd like to do today. So certainly you can stop me if you have some questions, and I'd be happy to answer individual questions. So here's what we were supposed to be looking at. We were going to see if we could understand and explain linear correlation, independent and dependent variables and types of correlation, and find the correlation coefficient. So essentially, the correlation coefficient is going to be a measure of whether or not there's a relationship between X and Y. So what we did is we made a scatter plot, and we looked at it, and we said, boy, it looks like these points are lining up along the line. Now, just looking at it is not a particularly strong measure. So we calculated the linear correlation coefficient. And while we didn't go into the details of the calculation, the mathematical details, we did determine that the correlation coefficient described the strength of our linear relationship. But that was for the sample of data that we had actually collected. So now it begs the question, if our sample, if our data values, if our points in our sample are lining up in a line, then would we expect the points for the whole population to line up in a line? It seems kind of like a reasonable assumption, but that's what we would like to test. So the larger the sample size, okay, the stronger the relationship then. In other words, the better the sample is at making a prediction about the population. So bigger sample is always better. But even for a reasonably small sample, we can say, you know what, if these sample values are really close to a line and really a strong linear relationship, then we would tend to expect that the population was also in a linear relationship. And we can measure the strength of that, right? We can measure the strength of how well our linear correlation coefficient for our sample predicts the correlation coefficient for the population as a whole. Okay, and we would call that a hypothesis test for the population correlation coefficient. And of course, then there's some details on how we might measure that. So let's go down. If you recall, our goal was to make a scatter plot. So here are some scatter plots: negative linear correlation, positive linear correlation, no correlation, some correlation, but not linear. Okay, and then we learned how to put these values into our calculator or Desmos and make a scatter plot, and then calculate the linear correlation coefficient. So there's the calculation. At this point, I'm recommending that you don't perform the calculation by hand, and rather just calculate R using your calculator or StatCrunch or Desmos or some other technology. You can, if you want to, run through this computation. And if you end up taking some more advanced statistics courses, we can dig into this equation mathematically and try to understand why this is the computation that we want for a measure that measures the strength of our linear relationship. But for now, we're just going to find R and then interpret its value. So the linear correlation coefficient then is going to be a number between -1 and 1 that tells you the strength of the correlation. And so 0 being there's no correlation at all, and 1 being there's exactly, the points line up exactly on a line. The negative has to do with the fact that either the line is going up with a positive slope or down negative with a negative slope. So here are some scatter plots that we could look at. Here, these points are lined up exactly on a line. R would end up being 1. Here, they're close to a line. We'd call it maybe 0.8. Here, they seem to just be spread out all over the place. And we would say weak correlation. It's about 0.45. I'd probably say no correlation here. Here, they're exactly on a line, but going downhill. So we have R as -1. Here, it's close to a line, -0.9. And here again, there doesn't appear to be any correlation. So the question is, now that we've found it, and here's 5 ways or 4 ways to find it. Here's Minitab, Excel, TI-84, and StatCrunch. So once we've found it, if I get that the sample is correlated with a linear correlation coefficient of 0.979, strong, right? Positive correlation. I'm wondering how much I can expect the population itself, the whole population, to be linearly correlated. Right? And so here's how you do the test. There are sort of a couple of ways that we might get after this. One is to use the data or the tables in the back of the book, which I generally don't recommend because then you need the back of the book and you have to drag it around with you all the time. I would recommend using a different technology. Today I'm going to demonstrate using the TI-84 on how to do the test. Okay, but you can either do it with the book or the calculator. And of course, there are lots of other technologies like StatCrunch and others that will also do the test as well. So first, what we do is this: we say we calculate, okay, our R, right, our linear correlation coefficient, and then we look in the table and we say, you know what? If it's close enough to 1, then we kind of feel like the population data is going to be linearly correlated as well. And for us, I think for this exam and for our understanding, I think that's probably enough. But if you want the actual numbers, then we can say depends on the number of data pairs. So if there's 5 pairs of data, which is probably not enough for a sample, but let's say you only have 5 data points. You go look at the table, you go find the size of the sample, and then you would say that at the alpha equals 0.1 level, in other words, to be 99% sure of a correlation, right? I would need R to be 0.959. Okay, so what was ours? Ours was I don't know what ours was, 97 something, right? Let's back up there, 979. And so we would say that since 979 is a little bit better than 959, that we would expect our population to have a linear relationship as well. Okay, if you want to be less sure or less confident, then at the 5%, it would take a smaller r. Okay, and then as we look further down, you might notice that, where's that bigger table? Here it is here. As we look further down and we get a larger sample size, then our value, okay, our regression value would be smaller, right? The smaller it is, even though we get a small linear regression, because we've got such a large sample, we expect the population to be linearly correlated as well. So you don't have to look up these values in the table. Of course, you can look up these values using the calculator, and I think we'll just do that here in just a second. Okay, so what do we do next? Next, we might want to do a t-test for the correlation coefficient. So without going into the mathematical details of why this is the test statistic, okay, you calculate the test statistic using this formula. And then you decide, is my test statistic rare enough, right, that I would reject the null hypothesis. In other words, the null hypothesis is that there's no correlation at all. And if there seems to be a strong correlation, then we say, well, there actually is one. We reject the null hypothesis and say there is one. So let's try this for the Old Faithful data that we saw last time. Okay, so I happen to type this all in. So what I'm going to do is just move over to the calculator. So I got to stop sharing. But let's look at this first. Using the Old Faithful data, 25 data pairs, we got R was 979. Is it significant? And we want to know at the 5% level of significance. Okay, so here we go. I'm going to stop sharing this, and I'm going to zoom in on my calculator a little bit, and we're going to see if we can make this thing work. Okay. Oops. All right. Well, come on, focus. I had some trouble last time with this thing not wanting to focus. Hopefully we can get it. It's like at some particular Zooms, it doesn't seem to want to focus for us. So maybe we can just keep playing with it and it'll come into focus. Okay, so here's what I did. I pushed stat, which is 2 buttons down and 3 buttons in, the stat button, and I put the data into the calculator. So this is the Old Faithful data that we were working with, and there should be 25 pairs. And since I was thinking that we might look at this again, I put it in, where did I put it? I think I put it in right here, list. That's the CO2 emissions. So here it is here in list 3 and list 4. So in list 3 and 4, I put the data so that I could still play with list 1 and 2 and answer people's questions, and I could kind of save it there for us. So here it is, right? This is the time between eruptions. Right? It went from about 1 to 5 minutes, and this was the time. L4 was the time between eruptions, and L3 was the length of the eruption itself. Question so far, stick the data into your list. The next thing that we wanted to do was make a stat plot. So push stat plot, it's second y equals, it's right here. You're going to turn your plot on. You're going to select scatter plot. And now that I've changed mine to list 3 and list 4, I'm going to have to say list 3 and list 4. You can certainly just use the default list 1 and 2. That'll work for you. Okay, so now I'm going to push zoom, and I'm going to go down to number 9, which is zoom to the statistics. In other words, fit all the data onto my screen. So that should look familiar. We made this one last time. There's our scatter plot. The question is, does it appear to be linear, right? Does it appear to have a correlation? And is it strong, medium, or weak? And is it positive or negative? And we'd say, well, it looks like a strong positive linear correlation to me. But it looks like it is not a very strong measure for math types. So they want to have a number that represents how strong it is. And that is our linear correlation coefficient. So we want to calculate R. Now to do that, we have to calculate our regression line. So to make a regression line through the data, we're going to say stat, and we're going to go over to calculate, and we're going to come down here to linear regression. So there are two. You can say AX plus B. This is sort of our standard way of writing it. We usually write the X's first. If you're a business major, right, and sometimes other statisticians, sometimes they like to put the constant first and say A plus BX. They're both lines. They both give the same numbers, except in this case, we've just written the constant, the intercept first, and then the slope. And the other way, we've written it in slope-intercept form. So whichever one works the best for you, that's the one we should use. So I'm going to use number 8 because it looked like the book was using 8 from time to time as well. Okay, so here we go, linear regression line. Now, it takes a couple of parameters. You have to tell it where's your data. And since mine's not in the default list 1 and 2, I'm going to have to say list 3 and list 4. Okay, mine's in 3 and 4. And then I'd like to tell it where should I put my answer when I get the answer. So I'm going to put my answer into Y1 so that I can graph the line. So to do that, I'm going to push vars, yvars, function, Y1. So what this says is do a linear regression on list 3 and 4 and put the answer into the first y equals equation. So here we go, boom. It says that the intercept is 33 or so and the slope is 12. It calculates the coefficient of determination, which we're going to see in the next section, and the linear correlation coefficient at 0.979, which is the same value we just saw in the notes. And not only that, but because we told it to put it in Y1, when I push Y equals, in Y1, it will have typed the equation for me. So notice that this is approximately 33 plus 12x. And then because we've used the calculator, we get much better detail than that. So then we can push graph. And we have our scatter plot with our line that we just calculated through the data. And we say, yep, it looks like those points are spread out pretty close to the line. Now, if you use the book to test the strength of your correlation, then you go look to see if a 0.979 is big enough for the number of data pairs that we have. If you want to use the calculator to do the test, then we're going to select stat and go over to test. So now which test is it? Well, you have to go way down near the bottom. Okay, we've done z-tests and t-tests and intervals and samples and proportions. And some stuff from chapter, I think that's 10 that we didn't quite get to. And then we have these two. Whoops, there they are. The linear regression t-test and the linear regression t-interval. So we can do a hypothesis test and we can do a confidence interval. And we're going to do the hypothesis test here first. So choose it. Where did we put our data? I put mine, it's a little inconvenient. I put mine in list 3 and list 4. So I'll have to change that. You can use the default. The frequencies are just 1. You could do this for grouped data as well if you like. And then you're going to test that rho is, in our case, not zero. In other words, if there is zero correlation, then the points are just spread out all over the place randomly. And so we want to make the hypothesis test that there is a correlation. That's our claim. And so our null hypothesis is that there isn't a correlation. And if there's enough evidence, we'll reject the null hypothesis. Notice that it also calculates the regression equation and asks you where you would like to put it. So we didn't actually have to calculate the regression line first. Doing the test would have calculated the line for us as well. And then we go down here to calculate and we say go. And it says, okay, here we go. Y equals A plus BX. Notice that it used that form. That's why I chose that form as well. We've got 33.68 and a slope of 12. So those are the same numbers that we got before. We got a coefficient of determination, R squared, of about 96%. And we got a linear correlation coefficient of 0.978, same number. And then up here, we have the results of our test. So we ended up with a test statistic of 22.8, okay? And the probability of getting that test statistic would only be 2.6 times 10 to the minus 17. In other words, 0.000000000, 16 zeros and a 2. Okay, there is not much area left. That test statistic is way, way, way over there. And so what should we conclude? We should say that at the 5% significance level, our correlation would be significant. Okay, and we would reject the null hypothesis and say there's a linear correlation. In fact, at pretty much any alpha level, right, all the way out to 10 to the minus 17th. Okay, so we would say, yes, this is a strong linear correlation. And I would expect that if we measured all of the times and every single time that Old Faithful erupted and took all the population data, we would get a strong linear correlation as well. So there you go, hypothesis test for a correlation coefficient. Notice it's very similar to other hypothesis testing that we've done before. The only things that we really didn't do is dig into the mathematics of the actual equations for calculating both the linear regression, the linear correlation coefficient and the test statistic T, right? So the mathematical formulas for those. And if you want to dig a little deeper, you're certainly welcome to, and we would explore those maybe in a more advanced class. But for now, I think let's just get our sort of our heads wrapped around the concept of what's going on and being able to use technology to interpret the results. Okay, that is testing of a correlation coefficient. Questions about that? All righty. Well, seeing none, I'm going to share the notes again with you. Make them a little bigger so I can see them. Okay. I much prefer the calculator method to the book. I don't like looking it up in the table. The table is only giving us 3 decimal places of accuracy and all that kind of good stuff. So, you know, so whatever. What did the book say? It had to be, for ours, it had to be bigger than 0.396 is what the book says. And ours came out 0.979, which is way bigger than 396. And so we say there is enough evidence, right, to conclude there's a significant linear correlation between the eruptions and the time between eruptions. Okay, so I'm happy on the test if you use the book or the calculator, but I kind of think the calculator is much easier. Here are the details of what we did, right? I sort of said these things out loud, and here are the notes. The null hypothesis that we tested was that there is no correlation, and the alternative is that there is a significant correlation. And then we did our sort of our two-tailed test. And here are kind of the details of how to go through that. And here's the value, here's the formula for calculating T if you want to do it by hand. Okay, so that was in 9.1. Then we went on and did, I still think Larson's approach was a little weird because, of course, we're testing the strength of it without actually putting the line there. And then he goes on to do the line. Okay, whatever. Here's the regression line. And then he says, here's how we build the regression line using this formula. Once again, I recommend using technology for calculating the slope and the intercept for the regression line. If you want to use the formulas, you certainly can. And I think it's beyond what, our mission right at this point to be able to say, well, why does this calculation produce the slope? Okay, and I think that's a very good question, one that you should definitely, if you're a math type, be curious about. But for us right now, let's just make this regression line and interpret it. And then when we have some more time in a future class, we'll go back and dig into why is this the right calculation? Why does this calculation produce the slope? Okay. So there's our regression line. Here's the one that we calculated. Here it is on the TI-84 Plus. I just did that with you. Here it is in Excel, so you can do it in Excel as well. StatCrunch and lots of other tools. Notice that here was our old faithful data, and this was the data that I stuck in list 3 and list 4, so you wouldn't have to wait around while I typed it in. Okay, there is the regression line that it calculated. I seem to remember, notice that it wrote it in mx plus b, right, slope-intercept form. When I did the calculation, I did b plus mx, right? I wrote this the other way around, but I seem to recall we got the same numbers. In fact, because we used the calculator, our slope and our intercept were to 10 places of accuracy instead of just 3. So be sure that when you're doing your MyStatLab homework or the exam, that you kind of read the directions and round off to the right number of decimal places. Unfortunately, Canvas is even worse than MyStatLab, and it doesn't do multiple answers real well. And so there can only be one answer. So we're going to have to say round to 2 decimal places, because if you end up rounding to 3 decimal places, even though technically your answer is more accurate, it doesn't know how to mark that as right and wrong. Okay, it'll just mark it as wrong. Okay, so that gets us down to the bottom. What can we do with this regression line now that we have one? And that's sort of our last topic. We want to do something called predicting the Y values. And then we want to know how accurate is our prediction. And so once we've found this regression line, notice that the regression line goes through the data. Let me put my graph back up. Our regression line goes through the data. Okay, here it is. But these points, right, these points miss the line. And so the question is, what about right in there? In other words, I know, put the data back up, I know that if it's 1.8 minutes of duration, it's 56, right? It's 56 minutes in between. I know that if it's 1.98, it's 57, and 2.05, it's 57. What if it were like 2 exactly? Or what if it was like 2.5 exactly right in here? And then the question is, can we use the line to figure out what those other values would be? And we call this, predicting Y values. And so there's a couple of things you gotta, so essentially you just plug in your X into the equation of the line and do the calculation. Here they say if you're interested in finding out how long you would have to wait for 2 minutes, you would simply plug 2 into the equation. Okay, and they get what, 58.6. So we could do that with our equation as well. On a graphing calculator, okay, you're going to just go back to your regular home screen, and you're going to say vars function y1. So you're going to grab y1 and using standard function notation, you're just going to plug a 2 into the y equation. And here it comes out 58.6. Okay, exactly the same as we just saw in the notes. The other way you could do that is if you're looking at your graph, you can push the trace button. It's along the top there, fourth one in. And then look, I can just arrow along. My line here. And so if I want to know, that's pretty close to 2.998. It says I'd be at 71 minutes. In fact, if you want to get exactly on 3, you can just type a 3, and you can say at x equals 3 at 71.12. So at x equals 2, it's 58.64. And so you could just do it right off the line, right on your graph screen as well. Questions about predicting a y value, plugging in an x and calculating a y. And one of the things that you need to be careful about is that this line passes through the data, but if you go, but our x's range from about 2 minutes to 5 minutes. So if you went way out here beyond the data, say at 30 minutes or something, then the line, okay, the end of the line tends to swing around quite a bit. And we would say that extrapolating beyond the data set is not likely to give very good results. Okay, so if you want to predict y values, predicting them within the range of the data set is fairly accurate, but extrapolating beyond the data doesn't give very accurate results. So yes, you could say, well, what if it was a 15-minute eruption? Then what would the answer be? That'd be way out here somewhere. And while you could calculate it, I don't know that it would be particularly meaningful. Okay, so where are we? There's the prediction. All right, then it says, all right, let's do some interpretation. So I'm going to go down to the very bottom for our very last topic. Here it is here. We want to construct a 90% prediction interval for, oh no, we switched to carbon dioxide emissions and off of Old Faithful. It would have been nice if we stayed with the geyser data so we didn't have to switch. But basically what it's calculating here is it's saying that I do my regression line again, but now I'm going to use the carbon emissions data. I'm going to get a regression equation. I'm going to predict the value at 2.8. So I stick in at 2.8 and it says I'd get CO2 emissions of 614.7 or so. Now the question is, all right, how accurate, right, is that prediction? And so we want to build a confidence interval around that prediction. And so to find it, we use this formula. Again, I don't think that at this point it makes sense to dig into the gory details, but you certainly can. If you plug in the numbers, you will get a margin of error, okay, for our prediction. And then, of course, the value minus the margin of error and the value plus the margin of error will give you your confidence interval. So I don't think that I would like to dig into the mathematics behind this formula right at this point, but just leave it with the concept of a confidence interval. In other words, I'm 90% sure that our prediction is going to fall in this given range. Okay. Now, here's some good and bad news. The good news is that this is way easier using a calculator. The bad news is that while the calculator has, at least the TI-84, has a lot of built-in calculations for statistics, it doesn't have this particular calculation built in. I think the newer TI Inspires and maybe some of the newer calculators do, but the 84 doesn't. And so what I did is I wrote a little program so that I could just program the calculator to do this calculation so that I wouldn't have to type in all these numbers and do this calculation by hand. So if you're interested in putting in the program, I sent it to you. Let's see, where did I send it? I sent it to you as an announcement, I think. Did I send it as an announcement? Yeah, so in the announcements are some programs right here that I wrote for the calculator. Notice that back in the day, in fact, I was using a TI-83. The TI-83 doesn't even have an inverse T function. So here's a little program for inverse T. The 84s all had an inverse norm and an inverse T. Here is the confidence interval for the slope. And here is linear regression y-t confidence interval. So a confidence interval for a predictive value. And right there, if you look carefully, this is the exact same formula that's in the book for calculating the error. So if you've programmed your calculator before, or if this sounds kind of interesting for you to explore, then you can program this into your calculator and it'll do that calculation. I would like you to try it, maybe just by hand. You can certainly try it by calculator if you wish, on a couple of homework problems, but I'm not going to put this on the exam. So if this seems like a lot of work or beyond the scope of what you're interested in, then we'll just leave it at the concept that there's a confidence interval around our prediction, and that's good enough. But programming the calculator used to be a bigger thing when the calculator was all the rage in technology. I would say that now the TI-84 is not the most prevalent technology for using. You might use StatCrunch. And this function is built into StatCrunch, so you wouldn't have to do the programming. But if you really like the TI-84 and you'd like to learn how to do some programming, you can Google how to program your calculator. It'll give you some step-by-steps, and then you can type this program in and test it out on that last problem. Okay, that I think should wrap up our notes. So let me go back to the notes and see if we're at the bottom. Yep, boom, bottom, that's it. Okay, so that is all the notes from chapter 9. I am not, as I already mentioned, if you can get your head wrapped around what we're doing here, the concept of what we're doing here, that's enough. And if you want to work through the numerical details, you certainly can. And if this giant calculation leaves you feeling incomplete, as in, why is this, why does this produce, why is this particular mathematics producing our margin of error? Why is this the formula? Where did the formula come from? Those are good questions for another day, for your next stat class. If you want to keep exploring these kinds of things, I think you're going to look at this again in Stats 2, right? But for those of us who are just kind of getting our feet wet, getting a little introduction, and then moving on, I think that if you understand that there's a sort of a margin of error around this estimate, and there's a way to calculate that, I think that's adequate for what we're doing right now. Okay, that is all that I have for you today. I wanted to save just a little bit of time in case there were questions about chapter 7 or chapter 9 that are bothering you before we take our test, or if there are questions about what to expect, right? We're going to, this is it now. I will be available during office hours, the rest of this week for sure, and I will be in and out, near my computer. I don't know, I'll sit there for the whole hour every time. So if you want to catch me at office hours next week, send me a note and I'll be happy to Zoom meeting with you so we can meet face to face, or we can just correspond via email next week if you have questions leading up to the test. Any questions, anything bothering you before we wrap things up?
No, I don't think so.
So I'm getting a couple of nopes. As you get working on the homework, if you do run into some particular problems, I would be happy to help you with those. And you know, as you get closer, as you're doing your studying, or as you're reviewing and going back and getting some more points from homework assignments that maybe you hadn't completed earlier, if you run into some problems there, I'm happy to help as well. So just send me a note, and we can either get together or correspond on the email. Okay, well, that's it for today. Good luck studying for the test. Let me know if you run into problems or questions. And I'm anxious to see you guys next Thursday. Remember to sign into the meeting so that I can proctor the test, and then we should be all
Awesome. Thank you so much.
done. Okay, talk to you soon.
Bye.
Thank you.